Okay, I want to spend some time here on ramp rate resiliency. And for those that are not aware, there are, and for the data center people on the call, I have bulked many different types of data centers into three primary categories: hosting, AI training, and AI inference. And I appreciate that that's a gross generalization of different types of data centers. But for the sake of this presentation, I wanted to highlight the three different types where you have relatively low volatility and relatively high load factor for the hosting. AI training can be high load factor, but for short periods of time, where there's other large amounts of time where the power or the data center is not running near full load. And this is where we're training models. And the AI inference data centers are where the trained models are being actively deployed. So, when I used ChatGPT to figure out certain aspects of how to respond to certain questions to this presentation, I was leveraging an AI inference data center. However, the big thing I want to highlight here is that there can be 30 to 70% transient or load steps intra-minute. So we can see, for example, a 250 megawatt power plant or data center could go between 30 to 40 megawatts up to 180 to 200 megawatts within minutes. This is what we talk about as a ramp rate. That ramp rate of load volatility is going to be very hard for a behind the meter application to be able to respond to. Here's three example daily load profiles. These are just examples, but we have the hosting a load profile. We have the AI training load profile. So you can see how it's relatively consistent for hours of the day, and then it drops. And then there's some sort of other training going on, and then it drops, and then another training. Whereas inference is highly volatile and based on how it's being used by its customers. And so you can see significant volatility. But what's also important is to note is if we've installed 100% power capacity and the power plant is only using 10%, there's all of this stranded either grid connection or power generation that is not being used during this time frame. Over here is just it's a distribution of where these particular loads are showing. So you can see the AI, the hosting load is relatively consistent in the 70 to 50% range, whereas both the AI inference and the AI training distribution are quite varied. Okay. What we did then is we compared the three behind the meter technologies if they were to be directly coupled to the load. And I want to just emphasize, we assumed that the load of the power plant would be directly supplied by the generation. And many people on the call will be saying you wouldn't do that. We'll get into that here in a second. And what we did was for the hosting load profile, we ran the turbine power plant with one extra generator, medium speed with one extra generator, and the Rolls-Royce 2.5 megawatt with an extra 5 generators, so that if we were to lose one, we had that extra reliability. However, what that meant is that we were running in an average turndown rate of 67, 84, and 92%. This ultimately impacts our fuel efficiency. And what you can see here is that and I mentioned this earlier, we limited the load steps to 10% just for ongoing operation, 15 to 20%. But the thing I wanted to point out here is that we had zero load exceedances. So the turbine plant, the medium speed and the Rolls-Royce solutions were able to handle the immediate load volatility of a hosting solution or a hosting load. When we get into the AI training load profile, what you start to see, these purple lines, these are load exceedances, where the power plant directly coupled to the load is not capable of handling either the inrush current or capable of handling the load decrease. And as a result, to protect the power plant, it would trip off. So in this average scenario, in this one day, you'd have 100 situations where the power plant would be turning off. Not exactly very practical. However, and even the reciprocating engines and the medium speeds also struggled. Where we also saw the same problem was on AI inference. And the point I'm trying to make here is that directly coupled, no power plant would ever be able to match the load or be able to meet the load volatility of these data centers. However, what I do want to point out is that because we have a higher number of units, what we're able to achieve is a higher overall load profile on the engines, which does give us greater load swing capability. And we're able to achieve a higher fuel efficiency and a lower overall plant utilization. They effectively have less equipment spinning of the overall plant. This will ultimately impact our economics that we'll show you later on. So we've talked about this concept of directly coupling. And in normal power infrastructure strategy, we've already talked about this slide. What you've seen is a load being conditioned by the grid. But what we're seeing here is a load profile that the generator can't handle. And so what you're seeing here is the generator can handle it up to here, but then there's such a large load swing here, or I guess it was this load here, that the generator has to turn off because it just can't handle this load swing. Same here, and then same here. And so these would be moments where we would trip the power plant off. Solutions to that, what we do traditionally, and what a lot of people are talking about doing is actually now it's the opposite way. Instead of protecting the data center from unconditioned power from the grid, we're actually needing to protect the power plant from the volatile load. And a special thanks to Michelle Chartier from WSP, who helped around this discussion, where ultimately what we need to do is use a battery to be able to handle these instantaneous load swings to ultimately smooth out this load profile for the power plant. So what we were able to do is we were able to take that previously directly coupled power plant to the natural gas, or sorry, to the data center. And by adding a 50 megawatt BESS, we were able to dramatically reduce the amount of load exceedances on all three scenarios. But most importantly, now what you're seeing is a average load on our engines versus other scenarios, almost 100%. And that's because we're able to run these units much closer. And the reason why these units are a little bit lower is because we're having to provide that extra power to the batteries to be able to respond to those swings. For the AI inference load profile, which again is much more volatile, we had to increase the battery even higher to 100 megawatts so that we were able to handle that extreme load volatility.